Jacob, it's not your name. Sometimes I do that, but it's not your real name, and no one knows that.
That's
What's
all right,
going
Tony.
on, buddy? I'm just, it's a little bit off. I'm a little off. Matinee pre-recorded edition, high-risk pre-recorded edition, I will say, because we are recording about a variable stellar situation. So, Jake, what the hell are we doing?
Yes.
Yeah.
Stars that go bump in the night.
Stars that go bump in the night. Yeah. So we have Dr. Gerard van Belle with us today, and we're going to talk about. I guess so. It's a nova, and we're going to talk about how that's not a supernova. Apparently, that's different.
Yep.
You're going to help us with that one. So I'm just kind of laughing because I want to just preempt this with telling everyone that we are way out of our depth on this. Anthony and I are coming into this with about 0.1 nano bits of information about how astronomy works. So we're gonna have fun with this one. Usually we try and pretend like we know a little bit about what we're talking about, but it's not going to be true today.
With astronomy, if we knew what we were doing, it wouldn't be called research.
There you go. Yeah. We're doing research. We're doing not primary research. We're doing secondary research today. Is what we're doing.
I always tell people when they ask, like, "Oh, you do space shows?" My line is always, "It's more rockets than black holes." And so this is in the other realm that I usually leave for everyone else to handle. So I'm
it's more plumbing than photons.
That's probably where I like to live.
I used to say it's more planets than stars for me. That's the one. That's the one that worked. But
Ooh, we can talk about planets too. Yeah.
Okay. Good. Yeah. So should we start with some drinks? Did you bring anything today, Gerard?
I did, actually. Having seen the show before, I knew that, it was I was eager to go on the show because it was an excuse to day drink. And so
yes.
I have some bourbon here from Woodinville Distillery in Washington State. It's quite nice. It's not too caramelly. It's a nice bourbon.
Okay. Wow. All right. A bourbon. We don't get a lot of those on the show.
Not this early.
Not this early.
We won't tell anyone. We're doing pre-recorded, so it's like 9 p.m.
That's
Nobody will
make
any inference by the sunlight shining in my window here that it's bourbon o'clock. Yeah, not a lot of brown liquors.
No.
A lot of beers.
A lot of beers.
Lots of beers.
Tim Dodd would hit a brown liquor.
Mm-hmm.
Yeah. Mm-hmm. But that's pretty strong. I fortunately, Jake, somebody in this house, I don't know who, because I'm the only one that would have done this, hid a space camper at the back of the fridge that I did not know was still back there. So I was ruffling through, and I was like, oh, shit, I still got a Boulevard Brewing space camper back there. So this is, after the Phillies did okay against Kansas City Royals, I figured I'd dip back into the KC Royals brand activation that they did with us because we're a valuable baseball marketing show.
Oh, there you go. Yep.
Official sponsor.
Yeah,
what do you got, Jake?
Person.
I have no idea what time it is in your house, so who knows what we're about to get.
Yeah, it's about 9 p.m. So I'm just going light today. I got a little bit of pineapple coconut juice with some rum and triple sec in it. So just a nice little afternoon sunshine drink, It's
wow.
It's near the end of the summer, so you got to soak it up, right?
That's right. Yeah.
Kind
of an islandish drink.
Mm-hmm. So we, Anthony, you said this was a risky event because risky pre-record because there's something going to happen, and so maybe Gerard, you'll tell us what this is first, and we're gonna hope and pray that between now and when we publish this, the event
2 days from now,
exactly happen. Yeah, we got a narrow window. I think we're okay, but anyway, tee us up here. What are we talking about?
Yeah, see, when you have predictions in astronomy, there are some that are like eclipses where it's like the shadow will cross your spot in the next 3 seconds. You can do that. And there are other predictions in astronomy where we're like, it's going to be plus or minus a few months and maybe years. And so our best guess is that this event will happen before September. But we're kind of working on limited data. So, and what the event is, a brand new star will appear in the sky for about a week, and it's not going to be terribly bright, but it will be bright enough to be seen with your eyes. And this is unusual. Stars don't usually just kind of come into existence and then go away. And in this particular case, this is a nova, a recurrent nova, and that's our little hint that we kind of know what's going on. Is since it's recurrent, that means it happens again and again and again. Some of them are easy to track. They're on kind of 3, 10, 20-year timescales. This one's on about a 78-year cadence. So the last time it popped off was in 1946, I think. And then 78 years before that. And so we think it's going to do that, and we think that there have been kind of some telltale signs that it's getting ready to do its thing. But yeah, give or take a few months.
You mentioned last week's show as if you had listened to us talk about religious nonsense with Casey Dreyer for like an hour.
Did.
You may have it upon my take that the Big Bang sounds like some bullshit that we just haven't figured out yet. And I feel similarly about this take that every 78 years, a new star appears for a week. We don't know when, but probably before September. It's like, you're really specific, very general, and none of this makes any sense. So what does it do in the meantime? What are the other 78 years? What is happening in that area of space?
So let's to explain that, maybe we can dive a little bit into what this thing actually is. And so the short answer to your question is that it's gathering wool. It's basically getting ready to do its thing once again. And so what this thing is, so we've been actually kind of wandering around this. The name of this thing is T Coronae Borealis, because like with phrases like Big Bang, astronomers are terrible at naming things. And so this star is in the constellation of Coronae Borealis, the Northern Crown. You can see it in the summertime right now when you go outside. And it's like a big old smiley face on the sky. So I would have called it the big smiley face, but it said it's the Northern Crown. There are a bunch of stars in there, and there are some that you can only see with a telescope. And so with some of these sort of things, astronomers start to revert to just kind of telephone book naming for these things. So this thing has T Coronae Borealis is the name. And it is actually like many stars that you can walk outside and see on the sky. It's actually two stars. It's actually two of them with a big buddy and a little buddy right next to each other. And this is a commonplace thing, but what's actually more interesting with T Coronae Borealis is both of them are kind of old. In fact, the one star has already kind of died. And when a star like our sun, and both of these are pretty much like our sun, when a star like our sun gets to the end of its life, the outer part of the star gets sloughed off into the interstellar medium, and it leaves behind a burnt out thermonuclear core. And it's run out of fuel. It's still warm, but it's not fusing hydrogen into helium or helium into carbon, nitrogen, and oxygen. It's done. It's a leftover campfire. And so its neighbor, though, is almost there. It's puffing up and getting to the point where the outer layers of the star are starting to get sloughed off as well. But it's getting gathered up by its older brother. And so this puts a cloak of new material on this burnt out cinder, and you get to a point where it actually can reignite and flare up, and it'll take the hydrogen that its younger sibling next door has dumped on it, and you'll have runaway fusion. About 5% of that stuff actually fuses of the hydrogen that's come off, and then the rest of it gets blown off into space as well. And so it's basically whatever the time scale is for that mass transfer to happen and accumulate on the white dwarf, the older brother, and then it'll flare up. It takes about a week for this whole thing to happen. All the material gets thrown away, and then the process starts over. So that's what you got.
So it has to gather. It has to gather the right amount of stuff first before it will ignite. Like it's not.
Yes.
It's just something that kind of smolders throughout the whole time. It just kind of chills until there's enough of it, and then all happens all at once.
Yeah. And astronomers don't quite understand exactly what it takes to spark it, but it does appear to be pretty regular, and that's why with this one, it's a bit of a metronome. We've seen that it happens on the 78-year time scale, and there are records of it going further and further back through the centuries, where there appears to be, records from antiquity of, hey, this thing appeared in the sky. And so what's special about this one, we know about, a few dozen of these things in our galactic neighborhood in the Milky Way galaxy. We know of a number of these, but this one, when it flares up, it actually can be seen with your eyes. The other ones we've detected with telescopes, and they're a little further away and a little fainter. But this one's near enough and bright enough that you can see it with your own two eyes. And it's kind of special that way.
That's wild.
Isn't it cool?
This is why I don't do astronomy, because it's too much for me. There's too much going on. There's too much going on.
It's just one star is a party crasher. That's it. We all know how that works.
So what happened when the dead Mooch star? What happened when that one went out the first time? Like, did the other star care, or did it just keep doing its thing, and then all of a sudden this new star was sucking material away at a regular interval?
So that's an interesting question, which astronomers actually kind of wrestle with, in the sense that if what we currently see is the burnt out cinder and its little brother, its younger brother, dumping stuff on, when the older sibling was doing its thing and dying, did it dump material onto its younger little brother? And it probably did. If it's, if the interaction is close enough for that to happen, there's going to be this back and forth of how the lives of the stars are, inextricably bound, like Romeo and Juliet, and they're both killing each other.
It's a very dramatic situation. I love it, man. Jake's not into this. I'm into this. It's a random appearing star. Yeah.
How close are these stars together? Like, the mass transfer it must be somewhere near each other.
Yeah, I mean they're much closer than, say, they're on a lot of stars you'll see are on the order of many light days apart. So thousands of astronomical units from one star to another, and these are much closer. These are kind of on the scales of our solar system, where the Earth is 8 light minutes from the sun. That's 1 AU, 1 astronomical unit, and it's going to be on the order of that scale.
Really, like 1 AU is the distance we're looking between these things?
For some of these things, yeah. It's amazing how some of these stars are very close together. That's actually an area that I study in general, from the standpoint of, there's been a lot of interest in extrasolar planets. Where do we find them? What kind of stars host them? If every other star in the sky has another star right next to it, if it has a stellar companion, what's the truncation radius? When you get them too close, where do you stop planet formation from the baby stars?
Sure.
And it looks like it's like on the order of 100 times the distance between the Earth and the Sun. So maybe twice as far out as Pluto. You get the gravitational influences of the star on each other disrupt the disks around the stars, and so you don't get planets forming out of the disks.
Yeah. Okay. Huh.
Jake. Yeah. All right. Sure.
Nick still.
I got it. I'm all over that.
It's funny to think about just that. I know, like what you said, like binary systems are a lot more common than we think, because we get this bias about, like, this is what our solar system looks like, and so this is probably what they all look like. But then you find out that we're actually kind of weird and special sometimes. And like the binary thing is one that always stands out to me. It's like, yeah, there's so many of these systems that have 2 stars, and like, I don't know. I think that's wild to think about. I keep thinking. I'll tell you a funny story about my childhood.
Please. This will be good.
No, okay. So when I was like, I don't know, a kid in Canada, we had this show. It was called
Star Wars. This kid lived on this planet Tatooine. It had
Canadian Star Wars.
Star Wars is coming. Star Wars is coming. It was like Quarks something. All my Canadian people are going to be really mad that I don't remember this. It was very
I'm half Canadian, so I'm half mad at you.
Quirks and Quarks with Bob McDonald?
Quirks and Quarks. That's the one. Yeah. Bob McDonald, by the way, the most Canadian name that exists. It's just too many of them.
Look at that.
So it was like this science show they did, and I don't think it was Bob McDonald at the time. Anyway, we're digressing. Okay, so this show, they got a question from a listener that was like, I saw Star Wars and there was a planet with 2 suns. Can that happen? And they did, like, let's find out. And they did like this whole simulation, and their result, the simulation was, no, it's unstable and it'll fall apart. We can't have binary systems. It's just science fiction. And then that like stuck with me for a very long time for whatever reason. And then now I know that like there's tons of them. So I'm like, where did they go wrong? Anyway, that's my story.
There's still
explain this 50-year-old Canadian radio show, please.
Yes. So there's still kind of oddballs as far as finding the Tatooine-like planets. And, we definitely find them. That's been one of the big findings from the Kepler spacecraft that launched, 15 years ago. But, they're the dynamics and how do you get something like that is a big question mark. And it's probably something like I was just describing, where you have stars and you have disks around the stars when the stars form. But in this case, they're actually born so tightly bound and so close together that you get a circumbinary disk. And that'll basically it'll look like the disk around the two stars are so close together, they're like a point mass. And so you can actually do that and not have things be unstable. But a lot of people are suddenly interested in this kind of thing with 3-body problem having come out. And,
yes,
and trying to figure that show out. And so all these dehydrated trisolarians flying around. So
I keep trying to find like images of this situation, and mostly what I'm finding is artist depiction. So I don't know if any of these are fitting your bill, right? Like, is this, are you digging this one?
Yep, that's pretty good. And I'm glad you're bringing up how these are typically artist depictions, because they're so close together. Conventional telescopes have a hard time looking at this and seeing it as anything more than just a point of light of two stars smeared together. The sort of telescopes that I work on are interferometers. You have multiple telescopes that are all working in unison. You bring the light together, you form a much bigger telescope. And so you can actually build these things such that it's still hard to peel apart these two, but when the explosion happens, you can at least see the fireball growing and see it getting larger and larger. We look for asymmetries in it because of how, maybe the disk is the explosion is preferential along that disk of accumulation. These are all things that we try to measure and characterize to tell us more about the actual physics of what's happening in the system.
That's what I was going to ask on how, when this phenomenon was discovered, what were the early findings that led us to understand this mechanism, that there were two masses there that were interacting in this way? Did we see one that was closer, that we could differentiate between the two bodies, or was this always something that is in this realm of like, these are tiny points out in the distance and we're, doing some modeling around it?
It was the latter. It was always tiny points. As with so many things in astronomy, a lot of the interpretation has come, at least through the last 100 years or so, has come through spectra, where you look at the colors of the light, you can actually maybe see some lines shifting back and forth, where that's the fingerprints of two things orbiting around each other. And then you can even see the lines that are associated with material being blown off in outer space when the explosion happens. There's a lot of, with spectra, you get a lot of information, but then you have to then twist it around to trying to come up with a picture in your mind of, what would generate spectra that look like this. And so, I always prefer this much more direct route of building fancy telescopes that can really zoom in and give you,
look at it,
a lot more detail. Yeah.
Is this something where like James Webb would help? Like, would that telescope be useful here or no?
Not enough resolution. You need one of the telescopes I'm thinking of is like the Georgia State Chara Array, which is up on Mount Wilson. They have 1 meter telescopes. They have 6 of them, but they're spread 300 meters apart. And so you synthesize a telescope that's 300 meters in size in terms of its resolution. And so if you had a star the size of an orange and it was in New York City, and you're looking at it with Chara back, overlooking Los Angeles Basin, you can read sun-kissed off of that orange. That's how much resolution a big telescope like that gives you. Gotcha. And so it's good for looking at these kind of phenomena where it's really minute detail.
Should have spent more money on the telescope, I guess. James Webb.
Yep. Well, so, we
more
do this
shields.
Interferometry game. We do this business with the arrays of telescope is because all the money's gotten vacuumed up by James Webb. And so if you want to build a big telescope, you have to do it on the cheap. And so we do this with small 1 meter telescopes, and then you use a lot of mirrors to bring it together. And so you can, you would never be able to afford a telescope that big, even if you had James Webb's budget. But
you were shaking it, trying to get money to fall out, but it was just bolts.
That's right.
Nuts and shit that fell out of the sun shield. There's got to be something in there.
Yep.
Yeah, I mean, the other thing that makes me think of is the I forget the name of the project to image the black hole.
Yep.
Where like the whole Earth was the telescope. Event Horizon Telescope. A great description of exactly the thing I'm talking about. That's a really way to not stick in my brain that very simple name. But that was the same theory, but like the whole Earth
things.
was the telescope, right? So that was.
Yeah.
So
the key
was that
difference-
task? Okay, go ahead. Yes.
I was just going to say so a lot of the techniques kind of got adopted between the two camps for that kind of thing. The key difference between Event Horizon Telescope and something like CHARA is the wavelength of operation. CHARA works in the visible wavelengths our eyes can see. The Event Horizon Telescope is more in the millimeter, and there's a key difference here, which is in the millimeter you can have these telescopes spread across the planet. You can collect the light, you can detect the light, and then after the fact you can mix it. And the catch is in the visible, because of kind of how quantum mechanics works and noise and this kind of thing, you have to collect the light very, very carefully, bring it back together and mix it first, and then you can detect it. Otherwise you lose the signal. And so with a optical interferometer, something that's working in the visible, all the telescopes are on the same mountaintop, and they all have vacuum light pipes around, and you have mirrors reflecting light.
I don't even know what that means.
Detector.
What is a vacuum light pipe? Please explain that, because that sounds also ridiculous. Is it like one of them bank tubes, but instead of money, it's light going shooting over the other one?
It's a lot like that. Yeah, whoa. That's a perfect. Yeah. So the idea is
by
that.
By the way, if you're Neil deGrasse Tyson, we've stopped dreaming. It's the bank tubes that shot money around. We've stopped dreaming. We don't have that kind of stuff anymore, and I wish we did. So.
Right, and I wish they had money coming out of them too.
would have been helpful. Yeah.
My local Costco still has those, so I don't know what you're talking about.
What comes out? Churros?
But yeah,
what's in it?
When light travels through air, especially coming through the atmosphere, it really kind of gets beat up. It's a lot like if you're trying to see a coin at the bottom of a swimming pool, it kind of dances around. It's kind of mushy. And the more effective thing to do is once you've collected the light, if you don't want to do additional damage and you have to throw it like 150 meters to the lab, you put it in a pipe that has had all the air sucked out of it. So that's a vacuum tube. And it doubles as bank tel.
You are the best describer of any person we've had on the show of all time. You are absolutely wonderful to listen to, because it just clarifies a lot of things. But
I'm making my pitch to be the resident astronomer here. So
yeah, I mean, congratulations. You are now in. So explain, that sounds a little bit like the fiber optic cable operation mechanism. Like we want to transmit this via something that is less disruptive.
Yes.
So how much better is a vacuum light pipe than a fiber optic? I don't know how this description is going to help me at all, but that's a question that came into my brain.
Okay. So fiber optics is actually the way that we would like to go with some of this stuff. Vacuum pipes are kind of klutzy. They expand and contract in the summer sun because they're sitting, out in the open. They will break vacuum from time to time, and so then you suck up all the air, and you literally sandblast all your mirrors in the tube if you break vacuum.
Okay.
So I don't want that to happen, but it does.
Sounds
happen.
good. Yeah.
Oh yeah. And so fibers would be great, but fibers don't quite work right because the fibers. What happens is when you have a length of fiber and you put the light in, it's not vacuum that you're traveling through. You're actually traveling through glass, and the problem with glass is that it has a index of refraction. The blue light travels through it at one speed, basically, and the red light will travel through at another speed. And so the light that pops out the end, you get this phenomenon called longitudinal dispersion, where it's smeared out the colors, and you can actually work with that if the fiber lengths from, say, telescope A to the lab and telescope B to the lab, if they're exactly the same, like to a micron. But that's tricky, and we're trying to get around that. There's other kinds of fibers that maybe help with that.
Didn't sound tricky until you said micron. I was like, just spool it up.
Well, so once you get to the lab, the distance that the light has traveled from the star or whatever you're looking at into the telescope, into either the fiber or the light pipe, back to the camera at the back end. If you're taking multiple telescopes and mixing them together, that distance has to be equal to about 5 or 6 nanometers. And so you take your human hair and you look over the width of the human hair, that's about 100 microns. Divide that by 1,000, and that's 100 nanometers. And we're working at, about a factor of 20 below that. And oh, this is great shit. So, sorry, I can't. So
yes, you can. That's the point of the show.
Okay, so we get to the lab.
I think anyone's listening to this that would be like, man, curse words is where I lost the thread. We just got deep down a vacuum light pipe description. Come on.
Oh, it gets worse. So when you have the light from the star getting to the back end, you may have a situation where telescope A is a little closer to the lab than telescope B. And for the light to mix together in such a way that you get a picture again, you have to equalize these path lengths to 5-ish nanometers. But the star may rise in the east and transit and set to the west, and so the light may arrive at telescope A first before it gets to B, until later in the night. Then it's traveling and hitting the other one first. And so we actually put the light down a path where it goes and hits a mirror on a trolley that we move up and down rails in real time, and we can position this. These rails
giant are equatorial mount, basically, right?
Yeah, these rails can be 100 meters long, but we position the mirror on that cart to 1 nanometer. Yep.
This is so ridiculous.
So you've been describing all this technology and then immediately telling us how it's not good enough, which is a wild thing to me. Is there any other industry where our ambition has so far outpaced our technology? We're just the next question we have to answer, we're going to need a telescope approximately the size of our own planet. So we're going to work on that, and then
yep.
I have a barbecue outside, and the quality of the hamburger it makes and the quality of the hamburger I want, they're pretty in line. There's no complaint. There's not any problem with the mismatch between capability and ambition there. It's not true with astronomy,
Yep.
And the detail at which how unhappy you are with it. This would be better if I could. This other very complex thing that sounds just as hard as everything else you just described to me. It's where you've stopped and where you are limited by the laws of either economics or physics is kind of funny from people like us who have no idea about any of this.
Well, we're trying to
how do you measure a track down to a nanometer? That's a question I have. How do you even know that you can position that within a nanometer?
So little did I know when I was in graduate school, I would be basically working on oversized railroad track, hobby railroads, where you do a lot of track straightening and you do a lot of work of pouring concrete and punching nails into concrete because you want stability, and you build these elaborate room within a room type things where you can control the inner room to 1/10 of a degree Celsius, because you change the temperature and the rails will warp, and there's a lot of systems that go into aligning things and keeping them stable.
I don't know. Jake's trying to get into astrophotography, and I think this might be realizing that he shouldn't go down that rabbit hole.
I'm not trying. This is why.
Oh, you're not. You've aborted? Yeah.
You're trying to convince me. I never started.
Yeah. I think astrophotography is like the snorkeling version of the scuba diving that Gerard's doing.
It is.
Though,
It is. Yeah.
So you're you could see some shit. You could peer down there.
It's more like spritzing my face with one of those Disney World spray bottles compared to scuba diving.
Yeah, that's awesome.
I mean, there's always those people that take it to the nth degree. You go from the snorkeling to the scuba diving, and suddenly it's let's do a night dive, and let's do a deep water dive. And,
underwater caving.
Nitrox. Yeah. Oh, yeah. Yeah. And so.
Underwater cave free diving. Yeah.
Mm-hmm.
Okay.
I got one other thing. If we want to back out of the vacuum light pipe discussion, So this happens every 78 years. How many? I don't know. We've done shows for 8 years, and it's the first time we've encountered this whole situation. So, how often does this occur elsewhere? How many do we know about?
Mm-hmm. We know of a few dozen of these. Yeah, in the Milky Way, in our own galaxy, and they occur with periods of, say, 3 years, 20 years. This one at 78 years is actually kind of a long thing. It's probably more of a function of those are harder to notice. Things that have a longer time baseline than that. And if you need a telescope to see them, telescopes have been around not so long in terms of looking at hundreds of years timescales for these things. So our roster is not that heavy duty with these things, as far as things we know. There are starting to be more telescopes deployed that are really focusing in on time variable phenomena, and so we may at least then start to notice these things, so that when they go off again in 80 years or 100 years, we then can say, oh, this one did that back in 2020, whatever. Yeah, so we have a dozen, 2 dozen of these that we know about, and that's just our galaxy. These sorts of things are going to get found sometimes in nearby galaxies as well. They make themselves known and kind of obvious with how they brighten up and then go away. And so that's kind of cool. There's, of course, a whole industry in astronomy looking not for these smaller recurrent novae, but supernovae, where it's a one-off deal usually, where the whole star, it's usually, it could be a pair of stars or a single star, but in supernovae, you usually have the whole thing be just destroyed. And it's on the order of 10,000 times, 1,000,000 times brighter when it happens.
That's what we're all waiting for Betelgeuse to do, right?
Yeah.
Oh yeah, whatever happened at that? We figure out what was going on there?
Yeah.
So it is thought that there was some kind of dust generation event. When stars are old like this, they're very cool, say half the temperature of the sun, which is starting to get into the territory where if you have any pollutants in the atmosphere, things that are beyond hydrogen and helium, like carbon, nitrogen, oxygen, you actually can get them to form into dust. And you get dust formation and at times potentially enough to partially obscure the star. And so this is what happened with Betelgeuse for the last few years. Was there was some kind of giant dust generation event. Part of the star got blocked out by that, and so there was this dimming, and now it's back up to normal. We have this is again one of these astronomer predictions. We have a good idea that it's going to go supernova sometime between tonight and 100,000 years from now. And so there you go.
Yeah, that is, and contrary to whatever thinks, that is soon. Like that's as soon as we can tell.
Blink of an eye.
Yeah. So how far away is this star?
The T Coronae Borealis. About on the order of 1,000 light years away. I think it's actually a little closer than that. It's one of the nearer ones, so a few hundred, I think maybe is a better number.
Because we were joking with Casey last week because we were like, we don't want this thing to happen in between pre-record and whatever, and he's like, oh well, it already has happened because it's far away. And now I'm doing the math. I'm like, it's probably happened like 10 or 15 times since it gets to us, right?
Well, so that's actually a fascinating thing to think about. Let's say it's 500 light years away. That means that 5 or 6 events, the light that is an image of these events, they're kind of all in a train heading towards us and will get to us eventually.
I don't like that
either.
Yeah. Wait, so remind me though. All right, in that train, remind me what is the theory on the last time this ever happens? The other star's gonna die, or it does the same thing at the end? Like, how does this whole situation end? With these two?
So the way it ends is little star next to dead cinder older brother. It'll eventually run out of material to puff off of its surface, and then it'll be just a leftover cinder as well, and you'll get 2 white dwarfs, that's what these cinders are called, just orbiting each other. I don't know if they're close enough for them to then in-spiral at some point, but this is one of these things that these gravitational wave detector telescopes are trying to do, is seeing merger events between these basically heavy chunks of leftover stars. The current gravitational wave detectors like LIGO and Virgo, they're better at seeing really heavy things crashing into each other, like a black hole collision. There are black holes, and then less big are neutron stars, and then less big than even that are these white dwarfs that we're thinking about right now with T Coronae Borealis. So I don't think a white dwarf merger can be seen by LIGO yet, but they're pushing on that to make that more routine.
One thing that's really cool about this, like these recurring events, like I think about this a lot with Halley's Comet, right? Which is kind of similar time frame, around the 80-year mark, that kind of comes in clockwork, and we get to kind of see it. Is that like that on that time scale, the last time it happened, we weren't in the space age. So like there either wasn't as much capability to observe it. Right. And so like now, like we're like going through a sequence of these things popping up where we actually get to like do some pretty cool stuff with it. I kind of thought that like Halley's Comet, like it was just a little bit too early. Like it came in the 80s last time around when I was born. And it was like, we had the space shuttle, but like, there just wasn't like, rapid kind of like being able to deploy stuff at high volumes really quickly. And the space missions for Halley's Comet kind of petered out. There was big plans, but then I think only Europe really pulled it off. Right. And even then it was like kind of far off. But the next time that Halley's Comet comes, like, I think it's going to be different. Like we should have way more capability on what to do in 2065 or whatever it is. Right. So this kind of feels like that, right? So this is the first time that we'll witness this with the telescope capability that we have right now, right? With all these, there wasn't array telescopes in 1946, I don't think.
No, and not even really electronic detectors. It was all photographic.
All the computer parts are all brand new, right? So yeah, that's kind of cool that we get to.
We were dealing with some shit in 1946 as well. Like
there was a few things going on.
A little preoccupied.
Money was tight in 1946 while we were rebuilding.
I do have to say the sequence of this one in particular gives me a little bit of heebie-jeebies, I will say, just based on it seems to line up very well with our particular country's period after it's went through some shit. It's 2024, it's 1946, it's 1866, it's 1787. I'm like, that seems like we have to assign a great calamity to right before, so we know like the next one will be right around when this is going to go again in whatever. I didn't do the math, but the late 2080s or early 2090s.
But you never know what the catastrophe is until you live through it, and then you're like, God, that was some shit.
That was really some totally different.
Hopefully the catastrophe was just the pandemic, and we're kind of done with that now.
Well, no, that's what I'm saying. This was the pandemic. Right? No, because it's always a couple of years later, right? It's like after there's been some resolution to the calamity. So my prediction is put this in the for when we're doing the show when we're 80, Jake, and somehow people are still listening to us, or we're just calling each other on Thursdays and yelling at each other for a while. This will be the next time will be like right after the Martian War for Independence. And then this one will go off. Yep. That's my prediction. Yeah. So you heard it here first.
Ice wars. Yep.
Yeah.
Battle with cyborg Elon Musk.
How did these get their name as recurrent novas? Which nova came first, I guess, is the and why was this one so underwhelming compared to the supernovas?
So this one may have been one of the first ones noticed because it is something you can see without a telescope. So this would have been, definitely seen by our forebears. And the fact that it happens over and over again, just a question of how good is the record keeping, I guess, from the 12th century to the 13th century and so on and so forth. With the actual supernovae, they can be really bright, but they're really rare. I mean, in the Milky Way, we get one every 100, 200, 300 years or so. And so, Kepler the astronomer, not the spacecraft, saw the supernova back in, 16th century, 17th century. And, he used up our chit for that part of the millennium, maybe. So... And, everybody went bananas in 1987 when supernova 1987A went off in the Large Magellanic Cloud, which is a satellite galaxy of us. So it's a little kind of dwarf galaxy that orbits the Milky Way. And but that was the biggest, nearest thing that had happened in any kind of modern astronomy era.
Modern telescope era.
Yep. Yeah. And even that, 1987 was really on the cusp of where... real modern astronomy was taken off like a rocket at that point, because that's around the era that a lot of the electronic detectors really came in. I mean, literally 1990. A lot of that push actually came out of the technology they developed for Hubble, where they're like, oh, we got a telescope up that we're going to put up there, but we need the best new modern detectors, and we're not going to be ferrying down photographic plates, which at some point was a plan, and how they were going to do telescopes. And even, the Astro telescope that they flew on the space shuttle with one of my professors from Hopkins, Sam Durrance, it used film. And it was just the most effective medium at the time. And that was, again, 1991 or so.
Now I'm remembering all those like early planetary missions too. Like the Soviets had the one that went to the moon, and the same thing. It had like inside the spacecraft was like a mobile development center, so it would like take the picture and then develop it and then like print it and then like somehow like scan that and send it digitally. Like it was like some wild thing they had to do to get just like this little printer in space or whatever it was. And then I'm thinking the spy satellites too. Those old Corona ones, they had to parachute down and catch it midair with the airplane so that they weren't captured. Oh yeah, the good old days.
The good old days. Right. The Cold War. Yeah.
Don't you wish we could catch like Dragon returning with an airplane on its parachute? That'd be pretty fun.
Oh, that would be cool. Yeah. Well, Rocket Lab was trying that with their boosters. Remember, they're trying to recover the boosters.
That's right. Yeah.
I'm sorry they didn't perfect that. That would have been awesome.
Yeah. I mean, it's better though that they tried once or twice. And were like, well, that was a terrible idea. We should not do that. Like, I'm kind of glad that one didn't die on the drawing board. That was not for the pilots. That was probably terrifying, but for everyone else involved, it was kind of cool to like, see them at least give it a shot. How exciting that was. But who knows? Maybe the BE-4s will get snagged that way off the Vulcan.
Maybe. But that'd be the ULA way, right? Just like send out a C-130 to go catch it or something.
Totally. Yeah.
That's their insurance policy for not getting more engines from Jeff. So, where are my engines, Jeff? Yeah.
They're out there. Go catch them. Here's a plane.
We should probably take some time to talk about your work and so you're with Lowell Observatory, I guess, right?
That's
right.
So
maybe tell us a little bit about some of the other stuff you work on there, and we can talk about. I mean, the Lowell Observatory is a cool place to even just talk about. So I don't know what's going on there. I mean, it's a pretty historical place. So
that's right. So it's this interesting set of bookends with Lowell, where we have a lot of history, but we're also doing cutting edge modern research. We have a really big public program with visitors that come up Mars Hill, where Lowell is at in Flagstaff. We get about 100,000 visitors a year currently, and that's with our current visitor center that's like 6,000 square feet. And we're going to be opening in November our new Astronomy Discovery Center that's 40-ish thousand square feet, much bigger than our current thing. There's a good image of it right there that went by. And that's it. And that's going to be very exciting to have a much bigger venue for people to explore the planets and see shows about the stars and that kind of thing. And so looking forward to that. There's on top of that, there's 24 researchers up here on the hill with me doing all kinds of things like looking at T Coronae Borealis or, designing next generation telescopes. I personally do a lot of telescope design and development. We have a interesting project we proposed for putting one of these interferometers, these distributed telescopes, on the moon and take advantage of the CLIPS program, basically catch a ride with a very small experiment, something you can fit on a tabletop, and demonstrate how it's much more effective on the moon to do this kind of thing, where you don't need these vacuum pipes because you already have a vacuum. And so, 95% of your infrastructure just went out the window because you don't have to build it. And there's some interesting advantages to operating in an environment like that where there's no atmosphere. So we're kind of having fun with ideas and working with partners. We actually submitted a proposal for that for the last call of a funding line at NASA called Pioneers. We were working with Redwire, an industry partner there. And I know you've had some Redwire people on this show and other shows, and they're great to work with, a lot of fun to work with. We've come up with some. What's fun about working with these new space companies is, they're game. They're game and good to go, and they'll give it a shot. It's a bit more of trying to dot your I's and cross your T's to get a company like Lockheed involved with this sort of thing, which also has a great development department, but they're a little more conservative about these things, and that's fair. It's fun to come up with some crazy ideas involving carts on rails moving at nanometer precision. It's like, let's put it on the moon. And so, it's the fun part is a lot of this stuff we can, especially with the moonlight stuff. This is the name of the proposal we want to put on the moon. It's a very small thing that would be a payload bay on Eclipse lander. So you can actually just build it in the lab and test it out. It's not any giant monster instrument.
Yeah.
And you can retire a lot of risk that way.
Iterate, yeah.
Yep. So
that's wild.
Yeah, so we've got a lot going on up at Lowell. It's kind of fun with that. But the really big 800-pound gorilla in our corner right now is this Astronomy Discovery Center that's opening in November. It's going to be very exciting.
Awesome.
We'll have a bunch of people there to open it up and cut the ribbon. It's fun.
It's a place I've always wanted to go, because it's like, if in the world of space, if my two interests are like, planetary stuff and then like shooting the shit on this show, like those are like the two things that define my love of space. I think Lowell is like a perfect intersection of that.
Also geology, like you're a big rock nerd, and it's like
yeah, exactly. Yeah. But just like the whole
Flagstaff is awesome. The first thing that I had two thoughts the first time I went to Flagstaff. One was like, why does everybody live everywhere else in Arizona? And number two, if I really needed to, this is a great place to like ride out an apocalypse. Like there's just all these, it's this lush forest and all these nice resources around here, and it's beautiful. But I guess everybody got a little sample of that 4 years ago. So
yeah. It's a nice place to be.
I just love the story of like the Percival Lowell story is like, it's so emblematic of like everything that we do here. It's like this guy who like goes on this crazy conspiracy theory about life on Mars and like is like publishing propaganda about it, and then he like builds this telescope, and it's such a weird story. Every time I read it, I just like giggle to myself because it's just like so bizarre and strange. And it's like part of the Mars identity now.
He was a little avant-garde, but you know what? What are we doing on Mars right now? Looking for life. It's come full circle here, so maybe he wasn't that far off base. Okay, maybe he was a little off base, but still,
not as bad as that other Italian guy,
Yeah. So, but we have the history at the Observatory of discovering Pluto, a very fine planet in the solar system, and that was. I actually, here's an interesting story. I was actually somewhat accidentally in the room in Prague in 2006 with a vote card, voting on this ridiculous definition for planet. And voting against it, mind you.
Yes.
And I would just.
Oh, let's get into it. Let's hear some stories from that room, because I don't feel like we've never delved too deep into that.
Oh my!
We've never had a primary source.
Yeah. You were in the room where it happened, quite literally in this case.
I can go on and on about this. So what was interesting is the meeting. So this meeting is of the International Astronomical Union, the IAU. And my best description of the IAU is they're kind of like the FIFA of astronomy.
A little corrupt, pretty big, makes a lot of decisions.
Yep.
So who is the IOC in their case that they feud with all the time?
Oh boy,
figure that one out. You can report back on that. You don't have to get on the spot about that.
So, but the IAU does useful stuff. Like at a meeting I was at recently, they have this triennial meeting every 3 years where they at the end of the meeting they go over resolutions where they will resolve a definition of some sort. Like a astronomical unit is 150,000 kilometers from the sun, and they'll work it out to 10 decimal places. And this is a useful thing because an astronomical unit is actually increasingly used as a ruler of distances between things in the sky. And so when I say an AU, the person in Japan who's reading my paper needs to know what is meant by an AU. So that's good. That's good that you do that. But the problem here is that the IAU wandered out of physics into metaphysics. And what I mean by that is you can define what an AU is, but can you really define what a ruler is? A ruler can be a yardstick. It could be a length of string. It can be a phase-stabilized laser metrology system that I used on my interferometer. You can't define what a ruler is in those sort of terms, and nor is it useful. But they tried to with the whole planet thing, and so there was this definition, which interestingly, coming into the meeting, there was a definition which was different than what was passed. Coming into the meeting, they had a definition which was not that bad, actually. And by not that bad, my ideal definition does two things. It conveys the physics, and I could describe it to a kindergartner. And so they had a definition which was basically big enough to be a ball. That's it, full stop. And that actually I can describe to a kindergartner, but it's also captures a lot of physics. So if you have a thing in space and you're throwing material onto it, eventually you'll go from like a dog bone looking asteroid to something that has so much material, its own gravity pulls it into a ball. And you start to get glaciers, you start to get differentiation. There's a whole lot of wrapped up in that. And it's a natural breakpoint in defining things between, say, the Rebel Pile asteroids that Bennu was and Rygu was, that was visited by Osiris-Rex and so forth. And so you get into a whole new thing. And so things like Pluto fall into that category, as does the Earth and Mars and so forth. And these things are all like each other. They're more like each other than Earth is like Jupiter, which is this big clot of methane. It was kind of a weird thing that at the meeting, the definition proposal got hijacked and rewritten kind of on the spot. And then suddenly there was this criteria that you have to clear your orbital zone, and nobody even knows what that really means. And and I can't describe it really to a kindergartner anymore, because some of these kindergartners, man, they're whip smart. When they come to meet an astronomer night at Lowell, and these kindergartners are like, well, if the Earth has cleared its zone, why did that asteroid hit Chelyabinsk? And so I'm like, good point.
Yeah.
And so
send this kid to the IAU. Get up there.
Exactly. So my vote is that there should not have been a vote at all, because
you were the jury nullification of the IAU meeting.
Yeah,
I love that.
We don't have a similar official definition for a star or galaxy, because we never really got worked up about that, and we did about planets. So maybe someday the IAU will grab the third rail again and realize that they can actually undo this problem, but we'll see.
That's actually a great thing that I've always thought about, of like, why I didn't even know how does this actually come into play in anyone's life, right? Like now they've decided, other than the culture war aspect of it and the angry Twitter wars or whatever when New Horizons is going by, what is the actual result of the vote? What is the effect of that? Nobody really.
Well, there are actually some real problems, I think, from the vote, which is, since Pluto and Eris and Makemake and Orcus and Sedna and all these things that we've been finding in the outer solar system, since those have been demoted, quote unquote, they're not on the official list. And that means they're not taught in elementary school. And that means elementary school teachers, who are great and love talking about this stuff because it's the easiest subject to teach to fidgety 8-year-olds, they teach the inner terrestrial planets, and then they teach the gas giants, and then they miss out on talking about an entire third of the solar system, the Kuiper Belt and the planets that are out there and that kind of thing, because it's not on the list. And
the third zone, yeah. It
is. It's a huge zone by volume. It's a big part.
Alan Stern from the back. The third zone.
Yeah. It's true. And and all these people are carping about, well, there's too many planets. It's like, look, my kids learn 50 states and 50 states capital. They're doing just fine, and yeah, it's not.
Well, that's also just smacks of us feeling like we need to know them all instead of look them up as well, right? Like,
yeah. Well, it's also such a silly argument, because it's just like, no, we have to change the curriculum because we're too dumb. 8 things, too many things. We're dumber than that. We need
We're going to shorten the periodic table because there's just too many elements.
Yeah, nobody needs the UUU label on their periodic table. That was just too cool looking.
Technetia. What's with Technetia?
You're only an element if you're helium and hydrogen. There we go. Astronomers win.
See, the periodic table, though, is a good example. I always loved that there's like, there were always a couple extra boxes. Like, we'll get around to those. We'll fill those ones in a little bit. Haven't done the work yet, but I'm pretty sure there's a couple that live there. I always loved that aspect.
Stability, yes.
Yeah. So that we should have a planetary table that's like that. Got the 8 filled in, and then there's just a whole shitload that are not. But even then, it's kind of funny, right? Because, all right, so are you a moons are planets guy? What's your If you had to vote,
What do you mean?
like if you had to vote, what is a planet? Is it the round thing? Are you still on the circle?
Big enough to be a ball.
Team circle?
And
ball.
And then importantly, and this is not even part of this IAU definition done in 2006, you have to talk about the low end, big enough to be a ball, but you'd also talk about the high end, which is not a star. And it's kind of obvious to say that, but there's actually a lot of subtlety in that, because there are some of these things that are overachieving planets and actually have fusion going on at the core for part of their lives. And so those are.
What about the other star from this Corona star or whatever? That's an underachieving star, and it's a star sometimes every once in a while for a week. What about that one?
That's now a leftover degenerate object, and so
it's a planet.
But there's even elements of this definition of orbiting. The IAU definition says must orbit the sun, not a star, the sun. So there are 8 planets in the universe. Even though we know of now 5,000 exoplanets out there around other stars and that kind of thing. And we know, very importantly, of a whole family of planets that get ejected from their stellar system and are wandering in the void. And this whole class of rogue planets don't orbit stars at all. And so that, saying it has to orbit a star, it actually is kind of not true.
Yeah.
So big enough to be a ball, but what about if something happens to be a ball? Because Osiris Rex booted a random happenstance perfect ball off of the surface of an asteroid.
If you make it into a ball like the Echo 1 satellite from 1960, that was the balloon, just make it an honorary planet. I don't care.
So I guess that's where I'm like, I don't know. Part of me feels like this whole thing is just a great piece of bait to get people who are astronomically inclined to eschew authority, and that's what they should inspire in themselves to discover anything great. So I feel like it's a little bit of a trap of like, do you also hate authority in this particular instance? Go discover something bizarre and bring up the spirit of those that have been burnt at the stake 400 years ago because of their discoveries in the astronomical sense.
Yes. Well, it fits very much in with, Lowell being in Flagstaff, which is in Arizona, because Arizona is very much the oppositional defiance kid when it comes to the states. It's just, tell me not to do it, I'm going to go do it. That's Arizona for you. And it's kind of, it really sums it up. My boss, the director of Lowell, he's always liked to point out, though, that this vote that happened was probably one of the best things that happened for Lowell, because suddenly it was getting talked about again, and how Pluto is a thing, and is it or is it not a planet? And this was discovered at Lowell. Come visit Lowell. Yeah, we have a great visitor center. Yeah, come see us. And so he was always very happy about that. And
there's no bad press, right?
Yeah.
No
talk good about me, talk bad about me, but God damn it, talk about me. Yeah.
Oh, that's funny.
Nice.
Wow. Okay. So,
so what it sounds like, we discovered the shadow government here. That you were in the room with the vote. And it did great for the Pluto. It seems like there was some agent provocateurs in the room at the IAU, is what I'm thinking.
Some of us were kind of trying to wave a flag and be like, we can always come back to this next time. We're really rushing it. And no.
Yeah, was there anything else important to do at that time, or was that just the one that they got caught on? What else? What was underplayed at that meeting? Based on your
what was next on the agenda?
I should know this because the Pluto resolution I remember very well is resolution 5A, because they took 5, which was okay, and then they really jacked it up. But I have no recollection what resolutions 1 through 4 were. It's probably more like, what's the definition of an inch and this kind of thing, which actually makes sense. So
the meaning of was number 6, but never got around to that. A couple years late on that one.
6 was a thing related to the Pluto thing about, do we call it a Plutino or a Plutoid or a Plutonium? It was all really bad and off the cuff and very poorly thought out.
And you came out with dwarf planet.
I know.
Yeah.
I mean, the word's right there in the name, dwarf planet, but it's not a kind of planet. So, yeah.
Well, I think what we've learned today is that vacuum light pipes are cool.
Yes.
The moon is a planet, and yeah.
Binary
and it's possible to adjust a cart on a giant train track down to a nanometer. That is physically possible. Yeah, I'll have to come see that.
Yeah.
No
It's
more
cool.
excuses
It's
for
really
people
cool.
who park wrong now. Yeah.
Jake, I think we should put Flagstaff on the list of off-nom meetups.
Yeah, I agree.
That we need to make happen.
We will be
that-
happy to give you
think
the
that would
red
be
carpet
awesome.
tour. Yep.
Sleep over at the Lowell Observatory.
Yes.
That
I don't
could
think
be
we
it.
would sleep if we were there, Jake. I have unfortunate news for you of what we would be doing instead at night is looking at telescopes that are epic.
Yeah,
So, yeah.
and drinking bourbon. Yeah.
Yeah.
Yeah, probably. Well,
Okay.
I'm sufficiently mind blown by this discussion.
Yeah, I'm sufficiently
All right.
overwhelmed. Yeah.
Gerard, you plugged the visitor center. What else? Anything else in particular you would like to point people at if they are
I got
not
a
partaking?
Twitter feed. I got a Twitter feed. That's Fringe Doctor. That's it.
Fringe Doctor.
Yeah. When you get the light to combine, it makes fringes, and so Fringe Doctor works with the interference thing. That's the main. There you go. That's me.
So it's not for your views on planet definitions. It's for something else. Yeah.
No.
There you go. Look at that.
Was his most recent tweet though. So
Look at that, big Pluto right at the top of the feed there. Love it.
It's that was just a PR godsend having that heart right there. It's like,
it really lived up to it. That was
yep.
did not disappoint.
Awesome.
Jake, what we got? We're going into a weird period here. What's remind me what's happening next week. I may or may not be there.
Yet. Yeah. You may not be here. So we're now on watch. We're on Anthony Baby watch at this point. So
I can't tell you when it's going to happen. It might happen before September. It's kind of where it's at right now.
And 100,000 years from now, you will have a baby.
It's as specific as every astronomer's description of events. Yes.
Yeah, my kid showed up early, so yeah.
Yeah. So so we have. I'm working on a couple things. I just don't know what it is yet. I was hoping to have it ironed out, but we're not there yet. So we'll get there. There'll be something.
There's a show. I may be there. Jake will be there, and that's what we got. This was awesome, Gerard. You are absolutely our astronomer in residence, and I learned a lot of things. So feel like you're going to be called upon a lot whenever we stumble upon news.
Okay,
I'm happy to be on call.
All right, y'all. Thanks so much for hanging out, and we'll see you soon. Bye.
Very good. Cheers.